Good morning all students. Welcome to third lecture of Power Generation Techniques. I am Poonam Diwan, Assistant Professor in the Department of Mechanical Engineering, Vishwavidyalaya Engineering College, Ambikapur. The topic of today's lecture is fluidized bed combustion boilers. So, let's get started. In today's lecture, we will go through the following contents: introduction of FBC, principle of fluidization, advantages of fluidized bed combustion, disadvantages of fluidized bed combustion, types of FBCs, atmospheric classic fluidized bed combustion system AFBC, atmospheric circulating fast fluidized bed combustion system CFBC, and pressurized fluidized bed combustion system PFBC. So, what are FBC fluidized bed combustion boilers? The major portion of the coal available in India is of low quality, high ash content and low calorific value. The traditional great fuel firing systems have got limitations and are techno-economically unviable to meet the challenges of future. Fluidized bed combustion has emerged as a viable alternative and has significant advantages over conventional firing system. It offers multiple benefits like compact boiler design, fuel flexibility, higher combustion efficiency and reduced emission of noxious pollutants such as sulfur oxides and nitrogen oxides. The fuel burnt in these boilers include coal, washery rejects, rice husk, bagasse and other agricultural waste. The fluidized bed boilers have a wide capacity range 0.5 ton per hour to over 100 ton per hour. Now, we will see the principle of fluidization. When an evenly distributed air or gas is passed upward through a finely divided bed of solid particles such as sand supported on a fine mesh, the particles are undisturbed at low velocity. As air velocity is gradually increased, a stage is reached when the individual particles are suspended in the air stream. The bed is called fluidized. With further increase in air velocity, there is bubble formation, vigorous turbulence, rapid mixing and formation of dense defined bed surface. The bed of solid particles exhibits the properties of a boiling liquid and assumes the appearance of a fluid, bubbling fluidized bed. At higher velocities, bubbles disappear and particles are blown out of the bed. Therefore, some amounts of particles have to be recirculated to maintain a stable system. Circulating fluidized bed. The principle is shown in figure. If sand particles in a fluidized state is heated to the ignition temperatures of coal and coal is injected continuously into the bed, the coal will burn rapidly and bed attains a uniform temperature. The fluidized bed combustion takes place at about 840 degrees Celsius to 950 degrees Celsius. Since this temperature is much below the ash fusion temperature, melting of ash and associated problems are avoided. The lower combustion temperature is achieved because of high coefficient of heat transfer due to rapid mixing in the fluidized bed and effective extraction of heat from the bed through in-bed heat transfer tubes and walls of the bed. The gas velocity is maintained between minimum fluidization velocity and particle entertainment velocity. This ensures stable operation of the bed and avoid particle entertainment in the gas stream. In FBC, turbulence is promoted by fluidization. Improved mixing generates evenly distributed heat at lower temperature. Residence time is many times greater than conventional grate firing. Thus, an FBC system releases heat more efficiently at lower temperatures. Since limestone is used as particle bed, control of sulfur dioxide and nitrogen oxide emissions in the combustion chamber is achieved without any additional control equipment. This is one of the major advantages over conventional boilers. Now, we will see the advantages of fluidized bed combustion boilers. Fuel flexibility, high efficiency, combustion efficiency of over 95%. Overall operating efficiency is 84%. Ability of burn low grade fuel. Pollution control. Sulfur oxides formation is minimized by addition of limestone for high sulfur coals. CaCO3 solid plus SO2 gas equals to CaSO3 solid plus CO2 gas. SO3 plus CaCO3 gives CaSO3 plus CO3. Low combustion temperature eliminates NOx formation. NOx formation takes place around 1500 degrees Celsius. Easier ash removal, no clinker formation, simple operation, quick startup, no slagging in the furnace, no soot blowing, provisions of automatic coal and ash handling system, provision of automatic ignition system, high reliability and low maintenance cost. Now, we will see the disadvantages of fluidized bed combustion. The only disadvantage is that a large amount of power will be required to lift up the silica surface. So, motor of forced draft fan will be twice bigger than that of other conventional system. Now, next we will discuss about the types of fluidized bed combustion boilers. There are three basic types of fluidized bed combustion boilers. Number 1, atmospheric classic fluidized bed combustion system, that is AFBC. Second one, atmospheric circulating fluidized bed combustion system, that is CFBC. And third one, pressurized fluidized bed combustion system, that is PFBC. We will discuss it one by one. First one is atmospheric classic fluidized bed combustion system, AFBC, or we can say bubbling bed. In AFBC, coal is crushed to a size of 1 to 10 millimeter depending on the rank of coal, type of fuel feed and fed into the combustion chamber. The atmospheric air, which acts as both the fluidization air and combustion air, is delivered at a pressure and flows through the bed after being preheated by the exhaust flue gases. The velocity of fluidizing air is in the range of 1.2 to 3.7 meter per second. The rate at which air is blown through the bed determines the amount of fuel that can be reacted. Almost all AFBC bubbling bed boilers use in bed evaporator tubes in the bed of limestone, sand and fuel for extracting the heat from the bed to maintain the bed temperature. The bed depth is usually 0.5 to 1.5 meter deep and the pressure drop averages about 1 inch of water per inch of bed depth. Very little material leaves the bubbling bed, only about 2 to 4 kg of solids are recycled portion of fuel burned. The combustion gases pass over the superheater section of the boiler, flow past the economizer, the dust collectors and the air preheaters before being exhausted to atmosphere. The main special feature of atmospheric fluidized bed combustion is the constraint imposed by the relatively narrow temperature range within which the bed must be operated. With coal, there is risk of clinker formation in the bed if the temperature exceeds 950 degrees Celsius and loss of combustion efficiency if the temperature falls below 800 degrees Celsius. For sufficient sulfur retention, the temperature should be in the range of 800 to 850 degrees Celsius. Now, in the next slide, we will see the general arrangement of AFBC boiler. AFBC boiler comprises of following system. Number 1, fuel feeding system. Number 2, air distributor. Third, bed and in-bed heat transfer surface. And fourth, ash handling system. Many of these are common to all types of FBC boilers. We will go through this system one by one. First one is fuel feeding system. For feeding fuel, sorbents like limestone or dolomite, usually two methods are followed: underbed pneumatic feeding and overbed feeding. Underbed pneumatic feeding, if the fuel is coal, it is crushed to 1 to 6 mm size and pneumatically transported from feed hopper to the combustor through a feed pipe, piercing the distributor. Based on the capacity of the boiler, the number of feed points is increased, as it is necessary to distribute the fuel into the bed uniformly. Whereas, in overbed feeding, the crushed coal 6 to 10 mm size is conveyed from coal bunker to a spreader by a screw conveyor. The spreader distributes the coal over the surface of the bed uniformly. This type of fuel feeding system accepts oversized fuel also and eliminates transport lines when compared to underbed feeding system. Now the second one is air distributor. The purpose of the distributor is to introduce the fluidizing air evenly through the bed cross section, thereby keeping the solid particles in constant motion and preventing the formation of defluidization zones within the bed. The distributor, which forms the furnace floor, is normally constructed from metal plate with a number of perforations in a definite geometric pattern. The perforations may be located in simple nozzles or nozzles with bubble caps, which serves to prevent solid particles from flowing back into the space below the distributor. The distributor plate is protected from high temperature to the furnace by refractory lining, a static layer of the bed material, water cooled tubes. The third one is bed and in-bed heat transfer surface. The bed material can be sand, ash, crushed refractory or limestone with an average size of about 1 mm. Depending on the bed height, these are of two types: shallow bed and deep bed. At the same fluidizing velocity, the two ends fluidize differently, thus affecting the heat transfer to an immersed heat transfer surfaces. A shallow bed offers a lower bed resistance and hence a lower pressure drop and lower fan power consumption. In the case of deep bed, the pressure drop is more and this increases the effective gas velocity and also the fan power. In a fluidized in-bed heat transfer process, it is necessary to transfer heat between the bed material and an immersed surface, which could be that of a tube bundle or a coil. The heat exchanger orientation can be horizontal, vertical or inclined. From a pressure drop point of view, a horizontal bundle in a shallow bed is more attractive than a vertical bundle in the deep bed. Also, the heat transfer in the bed depends on number of parameters like bed pressure, bed temperature, superficial gas velocity, particle size, heat exchanger design and gas distributor plate design. Fourth one is ash handling system. These are of two types: bottom ash removal. In the FBC boilers, the bottom ash constitutes roughly 30 to 40% of the total ash, the rest being the fly ash. The bed ash is removed by continuous overflow to maintain bed height. FBC boilers, Bureau of Energy Efficiency 147, and also by intermittent flow from the bottom to remove oversized particles, avoid accumulation and consequent defluidization. While firing high ash coal such as washery rejects, the bed ash overflow drain quantity is considerable, so special care has to be taken. Fly ash removal. The amount of fly ash to be handled in FBC boiler is relatively very high. When compared to conventional boilers, this is due to elutriation of particles at high velocities. Fly ash carried away by the flue gas is removed in number of stages, firstly in convection section, then from the bottom of air preheater, economizer, and finally a major portion is removed in dust collectors. The types of dust collectors used are cyclone, bag filters, electrostatic precipitators, or some combination of all of these. To increase the combustion efficiency, recycling of fly ash is practiced in some of the units. Now we will discuss the second type of FBC, circulating fluidized bed combustion, CFBC. The circulating fluidized bed combustion technology has evolved from conventional bubbling bed combustion as a means to overcome some of the drawbacks associated with conventional bubbling bed combustion. This CFBC technology utilizes the fluidized bed principle in which crust size is 6 to 12 mm fuel and limestones are injected into the furnace or combustor. The particles are suspended in a stream of upwardly flowing air, 60 to 70% of the total air, which enters the bottom of the furnace through air distribution nozzles. The fluidizing velocity in circulating beds ranges from 3.7 to 9 meter per second. The balance of combustion air is admitted above the bottom of the furnace as secondary air. The combustion takes place at 840 to 900 degrees Celsius and the fine particles less than 450 microns are elutrated out of the furnace with flue gas velocity of 4 to 6 meter per second. The particles are then collected by the solid separators and circulated back into the furnace. There are no steam generation tubes immersed in the bed. The circulating bed is designed to move a lot more solids out of the furnace area and to achieve most of the heat transfer outside the combustion zone, convection section, water walls, and at the exit of the riser. Some circulating bed units even have external heat exchangers. A CFBC could be good choice if the following conditions are met. Capacity of boiler is large to medium, sulfur emission and nitrous oxide control is important. The boiler is required to fire low grade fuel or fuel with highly fluctuating fuel quality. Major performance features of the circulating bed system are as follows. It has high combustion efficiency. Sulfur present in the fuel is retained in the circulating solids in the form of calcium sulfate and removed in solid forms. The use of limestone or dolomite sorbents allows a higher sulfur retention rate, and limestone requirements have been demonstrated to be substantially less than with bubbling bed combustor. The temperature of about 870 degrees Celsius is reasonably constant throughout the process because of the high turbulence and circulation of solids. The low combustion temperature also results in minimal nitrous oxide formation. More economic produces 75 to 100 tons per hour of steam. Capacity range is about 400 to 500 megawatt and that of FBC boiler is 10 to 300 megawatt. Number of feeding points is less because lateral mixing is done by high velocity fluidizing air. Now the third type of FBC is pressurized fluidized bed combustion system, PFBC. Pressurized fluidized bed combustion is a variation of fluid bed technology that is meant for large scale coal burning applications. In PFBC, the bed vessel is operated at pressure up to 16 to 18 bars. The off gas from the fluidized bed combustor drives the gas turbine. The steam turbine is driven by steam raised in tubes immersed in the fluidized bed. The condensate from the steam turbine is preheated using waste heat from gas turbine exhaust and is then taken as feed water for steam generation. The PFBC system can be used for cogeneration or combined cycle power generation. By combining the gas and steam turbines, In this way, electricity is generated more efficiently than in conventional system. The overall conversion efficiency is higher by 5 to 8%. Operating temperature is 860 degrees Celsius. The pressurized flue gases are cleaned off and are expanded into a gas turbine. In addition, the excess air requirements of the boiler are met by the gas turbine compressor. Power generated by steam cycle and that generated by gas turbine, which is of the order of 80:20. Advantages of fluidized bed combustion boilers. Number 1, high efficiency. FBC boilers can burn fuel with a combustion efficiency of over 95% irrespective of ash contents. FBC boilers can operate with overall efficiency of 84% plus or minus 2%. Reduction in boiler size. High heat transfer rate over a small heat transfer area immersed in the bed result in overall size reduction of the boiler. Fuel flexibility. FBC boilers can be operated efficiently with a variety of fuels. Even fuels like flotation, slimes, washer rejects, agro waste can be burnt efficiently. These can be fed either independently or in combination with coal into the same furnace. Ability to burn low grade fuel. FBC boilers would give the rated output even with inferior quality fuel. The boilers can fire coals with ash contents as high as 62% and having calorific value as low as 2500 kilocalorie per kg. Even carbon content of only 1% by weight can sustain the fluidized bed combustion. Ability to burn finest coal containing fines below 6 mm can be burned efficiently in FBC boiler, which is very difficult to achieve in conventional firing system. Pollution control. Sulfur oxides formation can be greatly minimized by addition of limestone or dolomite for high sulfur coals. 3% limestone is required for every 1% sulfur in the coal feed. Low combustion temperature eliminates nitrous oxides formation. Low corrosion and erosion. The corrosion and erosion effects are less due to lower combustion temperature, softness of ash and low particle velocity of the order of 1 meter per second. Easier ash removal. No clinker formation since the temperature of the furnace is in the range of 750 to 900 degrees Celsius in FBC boilers. Even coal of low ash fusion temperature can be burnt without clinker formation. Ash removal is easier as the ash flows like liquid from the combustion chamber. Hence, less manpower is required for ash handling. Less excess air. Higher CO2 in flue gas. The CO2 in the flue gases will be of the order of 14 to 15% at full load. Hence, FBC boiler can operate at low excess air, only 20 to 25%. Simple operation, quick start. Up. High turbulence of the bed facilitates quick startup and shutdown. Full automation of startup and operation using reliable equipment is possible. Fast response to load fluctuations. Inherent high thermal storage characteristics can easily absorb fluctuation in fuel feed rates. Response to changing load is comparable to that of oil fired boilers. No slagging in the furnace, no soot blowing in FBC boilers. Violation of alkali components in ash does not take place and the ash is non-sticky. This means that there is no slagging or soot blowing. Provision of automatic coal and ash handling system. Automatic systems for coal and ash handling can be incorporated, making the plant easy to operate comparable to oil or gas fired installation. Provision of automatic ignition system control systems using microprocessors and automatic ignition equipment give accident control with minimum manual supervision. High reliability. The absence of moving parts in the combustion zone results in a high degree of reliability and low maintenance cost. Reduced maintenance routine overhauls are infrequent and high efficiency is maintained for long periods. Quick responses to changing demand. A fluidized bed combustor can respond to changing heat demands more easily than stoker fired systems. This makes it very suitable for applications such as thermal fluid heaters, which require rapid responses. High efficiency of power generation. By operating the fluidized bed at elevated pressure, it can be used to generate hot pressurized gases to power a gas turbine. This can be combined with a conventional steam turbine to improve the efficiency of electricity generation and give a potential fuel savings of at least 4%. Now, we will see the difference between FBC systems to conventional boilers. Retrofitting of FBC systems to conventional boilers. Retrofitting fluidized bed coal fired combustion systems to conventional boilers has been carried out successfully both in India and abroad. The important aspects to be considered in retrofitting projects are: number 1, water or steam circulation design; number 2, furnace bottom grate clearance; number 3, type of particulate control device; fourth one, fan capacity; and the last, fifth one, availability of space. Retrofitting of a fluidized bed combustor to a conventional stoker fired water tube boiler may involve the replacement of grate by a distributor plate with short stand pipes for admitting air from the wind box located underneath, installations of stand pipes to remove ash from the bed, provision of horizontal hairpin tubes in the bed with a pump for forced circulation from the boiler drum, modification of crusher to size the coal or limestone mixture for pneumatic underbed injection of the mixture. It may be emphasized that conversion of a conventional coal fired system to a fluidized bed combustion system can be accomplished without affecting major changes. After making a cost benefit analysis, oil fired boilers can also be converted to a coal fired fluidized bed combustion systems. However, it has to be examined on a case to case basis. Fixing or bubbling and fast fluidized beds. As the velocity of a gas flowing through a bed of particles increases, a value is reaches when the bed fluidizes and bubbles form as in a boiling liquid. At higher velocities, the bubbles disappear and the solids are rapidly blown out of the bed and must be recycled to maintain a stable system. Now, we will compare the features of bubbling bed boiler and circulating bed boiler. Features of bubbling bed boiler. Fluidized bed boiler can operate at near atmospheric or elevated pressure and have these essential features like distribution plate through which air is blown for fluidizing, immersed steam raising or water heating tubes which extract heat directly from the bed, tubes above the bed which extract heat from hot combustion gas before it enters the flue duct. Circulating bed boiler at high fluidizing gas velocities in which a fast recycling bed of fine material is superimposed on a bubbling bed of larger particles. The combustion temperature is controlled by rate of recycling of fine material. Hot fine material is separated from the flue gas by a cyclone and is partially cooled in a separate low velocity fluidized bed heat exchanger. where the heat is given up to the steam. The cooler fine material is then recycled to the dense bed. Thank you.